Hi everyone. This video is over horizontal tangents and rates of change as they relate to calculus and derivatives. You can see the objectives here. So let's get started. You can see on this first example we have a parabola 2x squared minus 2. We are looking at this over the interval from 1 to 3 halves. When you graph this, you can see that this is a parabola that crosses the x-axis in two places. We also see here that it is decreasing to a minimum and then increasing after. If we were to look at the graph of the derivative of this function, we would be looking at the slope of the tangent lines. And we can see here that the tangent lines in a decreasing function, the slope is going to be negative. If we have an increasing function this way, we can see that the slopes of the tangent line, as they intersect this in one point only, is going to be positive. So a decreasing function, negative derivative slope. Increasing function, we have an positive slope. And then where it changes, here at this minimum, we have a horizontal tangent. Looks like that. Okay, so what we're looking for here, this then would be the horizontal tangent. The slope of a horizontal tangent is 0, so that would mean that that's the point on this graph, on this function, where the derivative is equal to 0. All right, so what we're looking at here to find a horizontal tangent was very easy to find it graphically. What we want to find, though, is we want to find it numerically. So we're going to take the derivative. This is our function, 2x squared minus 2. We're going to take the derivative, so that's going to be 4x. And then what we want to find is we want to find where this function, where the horizontal tangent lies. So where the derivative is equal to 0. Now, if we were looking for where the derivative was negative, right, we would be looking for where it was decreasing. And when we looked at the derivative when it was positive, we would look for where the function was increasing. But where we want is the horizontal tangent where the slope is 0. So we know that that would be where x is 0. So that's the x coordinate of where the point of tangency, that's what we're looking for, is the point of tangency, right? So we need to know where that is. Well, we're looking for that point right there. Now we have a graph, so we can look at it. We know it's going to be negative 2. But since we don't have a graph, like we might not always have a graph, we don't want to have to graph it, then I would just put the 0 back into the original function. Now we don't want to put it into the derivative because that's the slope. What we want is the y value. This is y, this is y prime. So if I put a 0 in for x, I get negative 2, and you know, it matches with what's on the graph. That's what we're looking for, is the point 0, negative 2. Now another type of problem that we've done is finding the average rate of change. And so you see that we have this rational function here, negative 1 over x minus 3, from the interval from 0 to 1/2. It's a rational function. It's got a vertical asymptote here and a horizontal one here, right? So we're trying to find the average rate of change from 0 to 1/2. So 0 to 1/2 is just this little spot right here. We're trying to find its average rate of change. Well, an average rate of change is just the slope formula, but we're trying to find the slope from 0 to 1/2. So we're looking for a secant line. So if we drew that a little bit bigger, you know, we've got this big curve here. Let's say that this is 0 and this is 1/2. So we're picking a point here, and we're trying to find its average rate of change between those 2 points. So that's what's going on with this function right here, a minus b. So this is a and this is b. That's the interval a and b. And then f is that. So we would have 1 over negative 3 minus 1 over, and that's 1/2 minus 3, so it's 2.5, 5/2, okay, over a minus b, so negative 1/2. So this is really just some playing around with fractions. Minus 2/5 over negative 1/2. And in the top I have 15. So I've got negative 5 minus 6. So negative 11. Negative 11 over 15. Flip it over. It's also negative. So I have 22 over 15. So the average rate of change here is 22 over 15. And that's how that goes. Now, instantaneous rate of change is a little bit different than average rate of change. Average rate of change is like a secant, or like backing the car out of the driveway, driving to school, and having, what is my average speed over that entire distance? Instantaneous rate of change is, what was my rate at a particular time during that ride? And so we're using the derivative to find that. And so over here in the corner, I wanted you to see that we have different ways of thinking now of the derivative. The derivative is very handy. It means a lot of different things. But it says the slope of the tangent line to the curve, that's one we've learned before, instantaneous rate of change, and the velocity all have to do with the derivative. All right, so find the instantaneous rate of change at the leftmost value of the given interval. All right, so I need to find the derivative. So I say y equals, because I need to rewrite it, x minus 3 to the negative 1 power. Okay, and I have to use the chain rule for this, so I'm going to do y prime is positive x minus 3 to the negative 2 times 1. So y prime is 1 over x minus 3 quantity squared. All right, and they want to know what is the instantaneous rate of change at the leftmost. Well, the leftmost value is where x is equal to 0. So y prime of 0 is 1 over, 1 over negative 3 squared, which is 9, so 1/9. So that's all you really have to do to find the instantaneous rate of change. Now, depending on when you're watching this video, we may not have gone over the chain rule yet. So when I made the video, we were actually working on the chain rules. So take a look at that. The key is not the chain rule, but the key to this is you took the derivative. So whether you know how to use the chain rule or not, don't worry, you can use the power rule when we're in class. Now here is an interesting problem. It says, find the equation of the secant line that intersects the given points on the function, put in slope-intercept form. Okay, so if you'll recall, what we had before when we had the average rate of change, it was f of a minus f of b all over a minus b, right? The average rate of change is the slope of the secant line. So when we're finding the slope of the secant line, we're actually just finding the average rate of change. So you see here there are 2 points given, 2 points given here and here. So the interval will be from -1 to -1/2, just the x values. Notice they gave us points, but they didn't give us the interval. So when we find the average rate of change, we're trying to find f of -1 minus f of -1/2 over -1 minus a -1/2. So it's a little bit different there. All right, so let's put that in. I have 1 over -1 plus 2 is 1, and then minus f of b, so 1 over, that would be 3/2, so make that 2/3, all over -1 plus 1/2, which is going to be -1/2. All right, so that's going to be 3/3 minus 2/3 is 1/3 times -2 over 1, so that's going to be -2/3. And that is the slope of the secant line. That's the slope of the secant line. So to write an equation, it would be y minus 1 equals, I just picked one of the points, -2/3 x plus 1. And then to put that in slope-intercept form, I think I'm going to just leave it in point-slope because I'm out of room here, but you could put it in slope-intercept form easily. All right, then B says find the equation of the tangent line with the leftmost point. Okay, instantaneous rate of change. So we already found that. That was from the previous screen. Y prime was 1 over x plus 2 quantity squared. And then leftmost point. So I'm going to put that negative 1 in for x. Negative 1 plus 2 squared is still just 1. So this would be y minus 1 equals 1 x plus 1. And then sketching the two. That's why they have you put it in slope-intercept form, is so that you can sketch it onto the graph. We had one very, 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 very similar to this one on a homework assignment, or we will have one on the homework assignment. So if you keep remembering that the slope of the secant line is the average rate of change, and the slope of the tangent line is the instantaneous rate of change, which is also the derivative, then you will these will be a lot easier to decipher. All right, so thanks for watching, and see you in class.